numerical integration. Sometimes some of the integrals, if the stuff we started with in the last section, you get to the point that you cannot do it by hand. Like almost no one can do it by hand. But we do not want to leave it without integrating. So just recall when we said f of x dx, this represents from A to B, represents the area under the graph of f of x from x equals A to x equals B. That's what this stands for or represents. So what we do is, as I said, sometimes it's impossible to integrate a function. So it's sometimes impossible to calculate. So what do? We can estimate using areas. So this is the idea. Let me explain. Let's say we have a function f with this graph from A to B. So what we are going to use is an idea that was discovered by a German mathematician, his name Riemann. So what Riemann did, he said, you know, instead of just saying I don't know how to find the area below this, because this does not look like a rectangle or a square or a circle or some geometric figure that we know the area for. So he said I can split this into rectangles of the same width. Let's say I want to make the width that much. And you go down and up, and then you go the same width down, 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 and like so. So he said, let me do it this way. And find the area of all these rectangles. You find the area of all these rectangles and add them up. So if I take the area of this, 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 and add them up. Okay, if we add them up, so add all the areas up, areas of shaded rectangles, then this gives us the integral from A to B of f of x dx. It's about the sum of all the areas of the rectangles. About, it could be a little bit less, or it could be a little bit more. And he found out the more the rectangles he split this region into, the more accurate the area is getting. And to start with this, how did he start with rectangles? So the first question people ask, how do I know the width of the rectangle? Where does it go? Like, how do I know it's 1 unit or 2 units? Okay, because the first thing is that we doing the sum of all of them. That's what this integral came from. This is the first letter S of the sum, the word sum, stretch S. So those are called Riemann sums. Riemann sums. Now let's see. What happened is the first thing, I'm going to look at another graph and show you how to start with this. Let's say we have a graph like this. It doesn't really matter. I'm just drawing any random graph. So it starts at A. This A, usually you call it x0. And let's say you start with on the left side and you draw a rectangle, another rectangle, another rectangle. So this is x1, this is x2, this is x3, x4, x5, and x5 here is B. So we find the width of the rectangle by calculating delta x, which is always B minus A over n. N is the number of rectangles. So usually you'll see it's given to you 4, 3, 5, whatever it is. In our case, we have 1, 2, 3, 4, 5. In this example, n is 5. In this example, n is 5. Okay, so that's delta x. Delta x is the width of each rectangle. Now, if I start to find the area, watch how we find the area of the first rectangle. It's important. So the width of each rectangle, as I said, it's delta x, delta x, delta x. All of them, same. So the area of the first rectangle, it's length times width. So the area of any rectangle is always length times width. Let's say the length or the width is delta x. So delta x is the width for each one of them. How's the length? So the length for the first one is this distance that I'm going to highlight. Do you see it? At x equals a. That's the length of the rectangle. So how do I find the length? To find the length for first rectangle, the length would equal f of that point, f of a. F of a gives you the height. It gives you the y value, right? That's the y value, f of a. If you want to find the length of the next rectangle, this one, so basically you want to find what this is, this vertical distance. That's f of x1. If you want to find the next rectangle, this, it's f of x2. You want to find the next rectangle that I'm shading, f of x3. And the last rectangle, it's f of x4. Notice I didn't use f of x5. So this is f of x0 or f of a. So the area here is estimated to be delta x for the first rectangle times f of x0 plus delta x times f of x1 plus delta x times f of x2 plus delta x times f of x3 plus delta x times f of x4. So I didn't use the last one on the right. Keep that in mind. So then look what we can do with this. We can take out delta x among all of them. And that gives me f of x0 plus f of x1 plus f of x2 plus f of x3 plus f of x4. This here, in general, for n rectangles, see the one I did earlier, it was 5. For n rectangles, we get this delta x f of x0 plus f of x1. It goes all the way, you know, if you draw the rectangles on a number line like this. The last one, we call it xn, means the one before that is xn minus 1. So it goes all the way, not the last one, but the one before the last one. This is called left in points, and that's why we use L sub n, L for left in points. This gives the approximation of the integral from a to b of f of x dx for n rectangles, where, again, delta x is b minus a over n. This is for the left in point. This means there's a right in point as well. What happens in the right in point? We call it Rn, is again delta x. In this case, when we started with the left in point, we skip the last one on the right. When we do the right in point, we skip the first one on the left. So if you look at the number line in the upper right corner of the screen, we're gonna skip this one, x0. So we start f of x1 plus f of x2 plus all the way, we go all the way till the end. And again, this will give us the approximated area under the curve. So that's called Rn. That's right in point. So this is the right in point. The first one was left in points. And to see how this works, let's try to approximate the integral from 0 to 2 natural log of x plus 1 dx by finding L sub 4, R sub 4, and their average. Okay, let's go over this step by step. L4, it means left in point. Use the left in points for n equals 4 rectangles. That's what this means. The first thing I always find is delta x, b minus a over n. A is 0, b is 2. Let's substitute them in. 2 minus 0 over n. N is 4. So that gives us 2 over 4, which is 1/2, or 0.5. And without drawing the graph, this is what I do. It starts at 0 is given. A is 0. This is a, or x0. x1 is add a half. So x1 is 0.5. x2 add another half. x3 add another half. x4 add another half, and that's the max. It's 2, up to 2. Do you see we have decimals here? Do you see where the decimals are coming from? That's where it's coming from. 0, 0.5, 1, 1.52. And notice if you look at these, we call them sub-intervals. We count them. There's 1, 2, 3, 4 of them. 4 sub-intervals. So I want to find L sub n, L sub 4. Remember, it's delta x, f of the first one plus f of the second one plus f of the next one and the next one. And you skip the last one. Don't do f of x4. See, there's 4 of them inside the bracket. Delta x is 0.5. We need to find f of 0, f of 0.5, f of 1, and f of 1.5. And you might say, where's f? Well, f of x is the function inside the this function that I'm going to highlight, this is always the one before delta x, that's f of x. Natural log of x plus 1, that's f of x. So to calculate this, f of 0 means substitute x0 into the function. That's the function. So you get natural log of 0 plus 1. Substitute 0.5 plus 1. Substitute 1 plus 1. Substitute 1.5 plus 1. And now you're going to use a calculator to put all of this into the calculator, see what you get. So we put that in the calculator and I got about 1.007. 1.007. That's the left endpoint. So that's the left endpoint. The right endpoint, it would go the same way, delta x, but we skip the first one. We skip the x0. So we do f of x1, f of x2, f of x3, and f of x4. We go all the way till the last one. So delta x, remember, 0.5. F of x1 was 0.5. x2 is 1. x3 1.5. And the last one is 2. Now we go to the function. Natural log of 0.5 plus 1. Natural log of 1 plus 1. Natural log of 1.5 plus 1. 2 plus 1. Of course, you can add those small numbers inside if you like. This is 1.5, natural log of 2, natural log of 2.5, natural log of 3. And we're going to put that into the calculator. So we got 1.557. 1.557. Now their average, you average them up, is 1.007 plus 1.557. This is from the left endpoint, L4. This is the right, R4, divided by 2. That's how we average them. So that gives me 1.282. That's the average. So find Ln, Rn, and their average for the definite integral using the indicated value of n. So what's the integral? Let's say it's 2x cubed minus x dx from 2 to 6. N equals, or let's make it 2 to 5. N is 6. So it's we're doing, remember, the both left endpoint and right endpoint. So always the first thing we do, find delta x, b minus a over n. A is 2, b is 5. 5 minus 2 over 6. 3 over 6, 1/2, or 0.5. I like to draw a number line. It's starting at 2, add a half, add another half, add another half, add a half, next one, 5, all the way to 5. That's the max. If you count those sub-intervals, you have 1, 2, 3, 4, 5, 6 of them. 6 sub-intervals. So now what we do is we find L sub 6. It's delta x times f of the first one, f of the next one, f of x2, f of x3. How many of them are there? So this is x0, x1, x2, x3, x4, x5, x6. So we go all the way to x5. We skip the last one. If you start on the left, you skip the one on the right. Delta x is 0.5. F of 2 plus f of 2.5 plus f of 3 plus f of 3.5. F of 4, f of 4.5. Remember, what's the function here? It's the one before the dx. It's 2x cubed minus x. It's a lot of calculations or computations gonna be here. Let's see. F of 2 means you substitute x2 like that plus 2.5. So 2 times 2.5 cubed minus 2. 2 times 3 cubed minus 3. 2 times 3.5 cubed minus 3 plus 2 times 4 cubed minus 4, 2 times 4.5 cubed minus 4.5. And we need to put all of this into the calculator. This should be a 2.5. And this is 3.5, 4.5, wait, no. This is 3, yeah, 3.5. Next one's 4. I got about 238.875, or exactly that number. R sub 6 is going to be delta x. We skip the first value of x0 and we do f of x2 all the way to f of x6. So this is 0.5. F of, we skip the 2, 2.5, f of 3, f of 3.5, all the way to f of, the last value was 5. Now we're going to substitute into the function. 2 times 2.5 cubed minus 2.5 plus 2 times 3 cubed minus 3 plus 2 times 3.5 cubed minus 3.5 plus 2 times 4 cubed minus 4 plus 2 times 4.5 cubed minus 4.5 . Okay, after we put this in the calculator, we get exactly 354.375. Now we find their average by adding them and divide by 2. 354.375, and the first one we found 238.875. It gave me 296.375. Okay, the next way we did left endpoint and right endpoint. Now we have what we call midpoint rule. The midpoint rule, it says this: if you start with x0, x1, x2, x3, all the way xn minus 1, xn. So instead of starting either from the left or the right, what you do instead, you take the midpoint of each sub-interval, as you can see, all the way to the last one. Okay, and the way we do this is this, I call it, let's call it x1 star, x2 star, x3 star, all the way to xn star. So now when I want to find or estimate the area from A to B of fx dx, we say it's delta x, and we evaluate the function at these points, at the midpoints. That's what we call the midpoint rule, all the way to f of xn star. Of xn star. So we can go back and use the same example, 2 to 5, 2x cubed minus x dx, and n was 6. Okay, we're gonna find the same one, find the answer to this. The first one starts at 2. Right, so delta x, we found delta x to be 0.5. So 2.5, 3, 3.5, 4, 4.5, to 5. We go to the midpoints of each one of them. The midpoint here is, if you want to find what that is, you average 2 and 2.5. So you add 2 plus 2.5 and divide that by 2. That's 2.25. You do the same thing for the next one. That's 2.75. 3.25. 3.75. 4.25. 4.75. So then that integral we're trying to find is approximated with delta x, which is 0.5. Evaluate the function at 2.25 plus f of 2.75 plus f of 3.25 plus f of 3.75 plus f of 4.25 plus f of 4.75. So we don't skip any values. And there should be 6 of them, because there's n equals 6, so there should be 6 values. Now this equals 0.5. We substitute that into the function f of x, which is the 2x cubed minus x. So 2 times 2.25 cubed minus 2.25. 2 times 2.75 cubed minus 2.75 plus 2 times 3.25 cubed minus 3.25 plus 2 times 3.75 cubed minus 3.75 plus 2 times 4.25 cubed minus 4.25 plus 2 times 4.75 cubed minus 4.75. So the answer is 292.687 or 0.8. That's the midpoint. Now let me scroll back up and see what we got when we averaged them. It was 296. Do you see the answer here? How close this to the midpoint? And just so you know, in general, the midpoint, note, always the midpoint rule gives the best approximation. Next one is called trapezoidal rule. So recall, a trapezoid is a quadrilateral with one pair of parallel lines. This is called base 1, base 2, and this is the height. The area of the trapezoid, 1/2 base 1 plus base 2 times the height. So if we have a curve like this, they started at A, and instead of doing rectangles, they did trapezoids. So let's say they cut it that way. So they go all the way up and connected there, all the way up, connected there, all the way up, connected. Let's say that's the last one. X0, X1, X2, X3, X4. So we're taking for 4 cases, 4 trapezoids. So we partition the region into 4 trapezoids. And we're going to find the area for each one of them. This is 90, 90. That's delta x, delta x, delta x, delta x. So delta x still b minus a over n. For the first rectangle, I'm shading. So this one on the left side, that's f of x1. That's base 1 for that rectangle. And this line here, that's base 2, which is f of x1. So if I want to find, and the height is delta x, that's the height. So the area of the first rectangle, 1/2, base 1 is f of x0, base 2, f of x1, times the height. Second rectangle, 1/2, f, base 1 now is f, for this rectangle is f of x1, then f of x2, times delta x. For the third rectangle, and then we're going to do the fourth rectangle. Both of them 1/2, 1/2. This f of x2 for this rectangle, the base 1, and base 2 is f of x3, all delta x. And the last rectangle, we do f of x3 plus f of x4, all delta x. Now we can add all of them up, so the area will be approximately the sum of all of these. 1/2 f of x0 plus f of x1 delta x plus 1/2 f of x1 plus f of x2 delta x plus 1/2 f of x2 plus f of x3 delta x plus the last one 1/2 f of x3 plus f of x4 delta x. We can factor out 1/2 and delta x, so delta x over 2. That'll leave f of x0 plus f of x1 from the first one, f of x1 plus f of x2 from the next one, f of x2 plus f of x3 from the third one, and f of x3 plus f of x4 from the last one. Notice these go together, these combine together. So in general, what we get the first one as is, and the middle ones all get multiplied by 2. 2 times this, 2 times the next one, 2 times the next one, and the last one stays as is. So the first one and last one are the same. First are the same, but the middle ones all are multiples of 2, always. And we proved why right now. So one thing, let me go back up. This here, because we found this is called M6. This is called M sub 6. M sub 6, M for the midpoint. M for the midpoint. Here, what I just did, what I found is called T sub 4. T for trapezoid. No, wait, how many we found? Yes, T sub 4. T sub 4. We can take an example to do this. Use the trapezoidal rule. To find T sub 6, an approximation of the integral 0 to 3, the square root of 1 plus x to the 5th dx. This one is almost impossible to do by hand. That's why we do, we try to find approximation for that. Always the first step is find delta x. B minus a over whatever number you have there. So they say T sub 6, so you divide by 6. So that gives us a half. That's delta x. Now you can put a number line. The first one starts at 0, and you're going to go a half, then 1, 1.5, then 2, 2.5, then 3. That's where we go from 0 to 3. Again, f of x here is the square root of 1 plus x to the 5th. So T sub 6 now, remember from the formula it says delta x over 2. Delta x is a half over 2. F of, see, it's the first value, so f of 0 plus 2 times f of the next one plus 2 times f of the next value, 2 times f of 1.5, 2 f of 2, 2 f of 2.5, and the last one, f of 3. This is 0.25. F of 0, you just substitute the 0 in. 0 to the 5th. 2 times 1 plus 0.5 to the 5th. 2 times 1 plus 1 to the 5th. 2 times 1 plus 1.5 to the 5th. 2 times 1 plus 2 to the 5th. 2 times 1 plus 2.5 to the 5th. 2 times 1 plus 3 to the 5th. One. So we got around 18.579. That's for this one. So the last one, there shouldn't be a 2 there. But we got this, right? 18.579. So now the answer would be different because we added a 2 there by mistake. So it's 14.674. So in general, we learned ln, that's for the left endpoint, Rn for the right endpoints, Mn for the midpoints, and Tn for trapezoidal. So again, this one gives the best approximation. For areas.